Welcome to Section 2 of the Micromachining Lab module, where we discuss background and theory in the micromachining process. After this section, you have learned how to calculate important process variables, mainly spindle speed and table feed rate for any micromachining application, as well as understand the differences between micromachining and its macro-scale counterpart. These that are mainly caused by the material microstructure, edge radius of the tool, and mechanism by which we remove material from the workpiece. The two process calculations that are associated in micromachining are spindle speed and table feed rate. When we look at spindle speed, it's the cutting speed divided by pi times the tool diameter. As for table feed rate, it's based on the spindle speed we calculated above, a chip load, which is the amount of material removed per cutting edge of a tool, and the number of flutes or cutting edges on your tool. As I mentioned on the previous slide, spindle speed is equal to cutting speed divided by pi times the tool diameter. At both the micro and macro scale, the cutting speed is dependent on the material and can assume to be constant. Therefore, the spindle speed is inversely proportional to the tool diameter. At micro scale, our tool diameters generally are smaller than 1 millimeter in size. Therefore, our spindle speeds can be on the magnitude of over 100,000 RPM. For comparison, macro-scale cutting processes typically range between 1 and 10,000 RPM. As we look into more detail on the table feed rate, we see that it's the product of the chip load, the number of cutting edges on our tool, and the spindle speed that we calculated on the previous slide. Therefore, at the micro scale, because our spindle speed is much higher, our table feed rates are also much larger than its macro scale counterpart. To help aid you with these calculations, please see the cutting speed calculator spreadsheet located in the module. One thing to note, however, is that this cutting speed calculator will output values in SI units, whereas most machines in America use traditional English units for the coordinates and table speeds. Now we shift our discussion to look at the differences between micromachining and macro-scale machining. To start this discussion, we first look at merchant circle analysis, which was developed in 1941 as a way to predict the forces in a cutting process. The key assumptions that were made in this analysis were a rigid tool and workpiece, an edge radius equal to 0, and a homogeneous workpiece material, and shearing being the primary form of material removal. However, at the micro scale, as we will see, many of these assumptions do not hold, and our force analysis has to be changed to account for these changes in the assumptions. First, we look at the material microstructure. At the macro scale, the material can assume to be homogeneous, and the bulk properties will dominate all cutting processes. However, at the micro scale, because our tool is on the same order of magnitude as the grain boundaries and the microstructure of the workpiece, we tend to see a heterogeneous structure when cutting material at the micro scale. Therefore, it's almost like we're passing through many different materials through one passive cut. As we look more deeper into the microstructure properties during a micromachining application, we see that because of the heterogeneous effect, we're going to see greater force variations than what we see at the macro scale. These greater force variations will lead to vibrations and an increase in tool wear, as well as to surface roughness and burr formation differences as we pass through the various grains of the material. Next, we look at the edge radius of the tool. Typical diamond tools in micromachining applications have edge radii of around 2 microns, which is around the same size as the grain boundary of the workpiece as previously described. Therefore, these edge radii will come into contact with various grains per pass of the tooth. The final difference that we observe between micro and macro scale machining is the material removal mechanism. Typically in macro machining, all the chips are produced through a shearing process. However, at the micro machining level, we see both plowing and shearing occurring. Plowing occurs when we cut below the minimum chip thickness, and instead of having the material flow up the rake face and shear off the part, instead we push it, which results in a higher specific cutting energy and generally poor surface finish and increase in tool wear, which we'll discuss later in the lab module.